I know, she's okay, guys, focus for me. It's been a rough day already, so just work with me a little bit.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 61. It's on kinetic reaction control. Or more appropriately, it's comparing that to thermodynamic reaction control. Lots of times in a process, a spontaneous process, there's a choice that's being made. And depending on which path we take, we may have different products. And so it's kind of confusing, and I wanted to start with an analogy. Imagine if I asked you to buy a car, but I only gave you two places that you could go. You could either go to kinetic used cars, or you could go to thermodyne new cars. And so you're going to have to make a choice. And depending on which choice you make, you're going to get a different car. If you go to a used car dealership, you might get a car that looks like this. And if you go to a new car dealership, you're going to have a car that looks like this. Now, there are going to be advantages of both. In other words, what's the advantage of buying a used car? It's going to be super cheap. It won't be as expensive, but you're going to get a different product. If you have enough money, it's better to get a new car because that new car is going to be more reliable. And so this choice is also being made in spontaneous processes. In other words, there's control. And so it could either be kinetic control, and that kinetic control lots of times is based on activation energy. It's the cost of that process. And then we also have thermodynamic control. What's governing that? That's going to be the change in free energy, or our delta G. How much difference in free energy is there between the reactants and the products in this downhill reaction? And so let's go back to the cars for just a moment. So if we start with that cheap car right here, what's the advantage of that cheap car? It's going to have a low cost, but it's also going to have a low reliability. If we have that more expensive car, it's going to cost us more money to begin with, but it's going to be more reliable over time. And so what's governing that choice is really cost. If we don't have the money to buy a new car, then we're simply not going to be able to buy it. But if we do have enough money, it's better to buy that new car because it's going to be more reliable over time. And so what's really governing this choice? It's going to be that initial cost. Money is determining the path. Now let's stop talking about cars and then apply this to chemistry for a moment. And so in a free energy diagram like this, we start with our reactants. And so let's say we have this one pathway where we have reactants and products, and then we have another pathway like this. What are we getting? We're getting different products of it. So what's going to govern the difference between these two pathways? Well, it's going to be the activation energy. It's how much energy we have to put in to get that reaction going, to achieve that transition state. If we don't have enough energy to reach this transition state, then we're going to have to take this lower pathway. Our products are going to have less stability. They're going to have less energy in them. So what's governing the other pathway? That's going to be our change in free energy. We would like to take that pathway if we could. We'd like to have more stable products, but we can't unless we achieve a high enough activation energy. So what's really determining the path? A lot of the time it's the temperature that we have. And so let me give you an example of that. Let's say we have this reaction right here. We have our reactants on the left side and we have products on the right side. But let's say this product is less stable than this product. Well, if we're looking at this chemical reaction at a really low temperature, you can see that we're getting really low amounts of that more stable molecule and high amounts of the less stable molecule. Well, what do you think is going to happen if we increase the temperature? So we're increasing it almost 100 degrees, a little over 100 degrees Celsius. What's going to happen? Well, we're able to create more of that more stable molecule. Why is that? We're taking that thermodynamic pathway. We're taking that new car dealership pathway. And so in that first process, again, there was kinetic control going on because we didn't have the energy. We didn't have the money to take that path. But if we do, it's more advantageous to take the thermodynamic path. And so again, can you explain why a thermodynamically favored reaction may produce varying amounts of products? Again, it determines on...
All right, so that, sorry, it's at the very bottom. I'll read it off if you can't see it. You need to kind of be able to explain and also just understand that it is possible to create different amounts of different products at different temperatures. So you can create different amounts of different products at different temperatures. Different amounts of different products at different temperatures. And so the example where he had just previous, well, I'll read this off, but you can't see it still. So this kinetic control, thermodynamic control thought or theory is going to help explain why a thermodynamically favored reaction may produce varying amounts of products. So even though, yeah, it is still favored, it's definitely spontaneous. At different temperatures, you're going to make 10% of product A and 90% of product B, or at a different temperature, you might make 90% of product A and 10% of product B. And it's just because of the inherent stability of some of these molecules. If it's a very complex molecule versus a very simple molecule, they can be more stable at different temperatures. And so this different theory called kinetic control and thermodynamic control is what we're using to explain that. And so that example he just had it here where I think it was just right here, you can see that under low temperatures, kinetics is controlling the amount of product that's formed. So kinetics, the ability to reach that activation energy is going to create just a little bit of the stable product, which means high potential energy, okay? And a lot of the less stable product, because you don't have enough energy to only shoot all the way down to the exothermic, very, very low potential energy product. Low potential energy is a good thing because you don't have as much pent-up energy inside of you, so you're more stable. So the thermodynamic control is the part right here where you have the high temperature, and so that's allowing for a lot of the energy to be exothermically released, so you're going to make a lot of the stable product and very little of the less stable product. So they're opposites in the amounts that they create. Questions on the product stability thing? Okay, and I just took a couple notes here. So I don't know if you guys see this, maybe some light on. Can you see it? Okay. So kinetics is based on activation energy. That's under kinetic control. Thermodynamics is based on the Gibbs free energy. That's what endergonic and exergonic refers to, the free energy that's put out. Which of these is spontaneous, negative, or positive delta G? Negative. So the more free energy put out, the more stable the system. So this one he was referring to like an analogy of low reliability versus high reliability. So kinetics, low reliability, because not always are you going to produce a very stable product, like a stable car, a used car. This is example. So low reliability because it's going to make a less stable product usually. And then thermodynamic control is usually a high reliability analogy here because you make more of the more stable products, or just more stable products, period, depending on if you have multiple products made. And then temperature is going to be a big factor in determining whether you go with kinetic control or thermodynamic control, because temperature provides kinetic energy to a reaction. And that also relates really keenly with the Gibbs-Boltzmann equation, delta G is equal to delta H minus T delta S. All right, so that if you like, if you want to rewatch this, it's just called kinetic reaction control. It's under Bozeman Science. You can find it if I can find it. You're savvy. Okay. So this one is referring to coupled reactions, like coupled reactions. And it's relating back to thermodynamics a little bit too, and spontaneity. So it's driving non-spontaneous reactions. So if a reaction is non-spontaneous, it's generally just not going to occur. However, some very, very, very important reactions that we need to have in our body, they're non-spontaneous. Well, they're really important. We need them to occur, so we need to find a way to help them occur. We need to find a way to force them to occur. And this is called coupled reactions.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 60. It's on driving non-spontaneous processes. Again, those are processes that don't occur without external energy. We also call them thermodynamically non-favorable. Sometimes we call them endergonic. But if we were to look at a free energy diagram like that, we're essentially looking at an uphill reaction where we have a positive delta G. If we shove on it, it's just going to return to where it was before. And so how do we lift that? In other words, how do we lift that when the reactants actually have less free energy than the products do? Well, there's two ways that we can do that. First of all, we could add energy from the outside. So this is just a model, but if we add energy from the outside, then we can lift those reactants and eventually have the energy of the products. Where's that energy coming from? It could externally come from electricity, for example, when we're charging a rechargeable battery, or it might even come from the sun. And so that's how a solar panel works, or how a leaf works if we're looking at photosynthesis. Another way we can do it is we can couple it to a spontaneous process. And so if we were to look at an exergonic or an energy releasing process like this, where delta G is less than 0, that's going to be a downhill reaction. reaction. So you could imagine if we were to couple those two together, and again, this is just a model, then we could take some of that energy released in that spontaneous reaction and use it in the non-spontaneous reaction. So again, in a non-spontaneous process, our delta G is a positive value. So our goal is to make it a negative value. In other words, make this spontaneous. We can do that in one of two ways. We can take energy in from the surroundings. So for example, if we use electricity, like when we're charging a battery, then we can change that delta G to a negative value. Likewise, if we were to take in light, for example, in photosynthesis.
Is this flow map on your notes? Do you guys have your packet of notes available? I'm pretty sure I copied this flow map on there, just in case you're like one of those people like, I need to scramble and write everything down.
Yeah, it's on there.
Is it on there? Okay, you're welcome. All right, so if you need to sketch anything on there or write anything on there, it should be on there. It's right above the unit review. You see it? Right beside it? All right, cool. So you can see the non-spontaneous reaction generally would not occur unless you couple it with one that will kind of give it a little oomph to get started with, because it itself is releasing excess amounts of Gibbs free energy or just energy in general. Or you can provide energy from an external source, which is what photosynthesis is commonly going to be used as an example for. This photosynthesis is using light as an external source to force the reaction to occur, because the first part, light reactions of photosynthesis, are non-spontaneous, but we definitely need it to occur, so therefore light is required for that reaction to occur. And then electricity is another example of an external source of energy.
We can turn that upside down as well. We can also couple it to another reaction or to another process. So for example, in our body, we constantly do this using a molecule called ATP. Every time we convert ATP into ADP, we release a little bit of energy, and we use that to do things like think and move and talk. And so let's start with the electricity. So if we're looking at a battery like this, why does a battery eventually run out? It's because our reactants had more energy than our products do. And so we're losing that energy. Now we're using that to do work, we're using it and losing it as thermal energy, but eventually you have a battery that doesn't work. And so how am I going to recharge it? I have to connect it to electricity. And what that electricity can do is it can actually turn those products into reactants and then add energy to them, and we can recharge that battery so we can use it over and over again. Likewise, if we look at life on our planet, most of us are heterotrophs. What does that mean? We take energy in our food. So we take energy in our food, for example, like in glucose, we combine it with oxygen, we make carbon dioxide and water. But when we do that, the reactants, in other words, our food and our oxygen, have a higher amount of free energy than the products that we produce. And so we would be stuck if it weren't for the autotrophs, if it weren't for plants. What they can do is turn that backwards. In other words, they can take that carbon dioxide and water, and they can add energy to it. Now, where are they getting the energy from? They're getting it from the sun. And so how does photosynthesis work? Well, inside a leaf, you have chloroplasts, and inside the chloroplast, you have a membrane like this, and what it's doing is it's taking in energy from the light. What's it doing with that energy? It's getting its electrons excited. It's passing those electrons down an electron transport chain, and eventually those high-energy electrons go back into your food. Now, who are they making that food for? Themselves, because they're going to do that same process of respiration. Now, whereas a lot of that energy goes to this where does it go? A lot of that energy goes to this molecule right here, ATP, which is used in energy coupling inside our body. And so again, we're using external energy to turn that endergonic reaction upside down. Now that's one of only two ways that we can do this. We can also energy couple, and so what's going on there, we're taking an endergonic reaction and coupling it to an exergonic reaction, or pairing a non-spontaneous with a spontaneous reaction. So inside our body, the molecule that we use over and over and over again is going to be ATP, or adenosine triphosphate. And on the end, it has these three phosphate molecules. And as this last phosphate pops off, it releases energy with it. And so that's going to be a spontaneous reaction. It's releasing energy. But then we can break our food down. And as we do that, that releases energy, which we can use non-spontaneously to create more ATP. And it's said that you go through your whole body weight in ATP every day. Now, what do we use that ATP to do? We use it to couple to non-spontaneous reactions inside our body. So, for example, how do your nerves work? If we look at the lining of a nerve or the membrane of a nerve, we have the spontaneous release of the phosphate as we break down ATP, but we're using that for a non-spontaneous movement of ions inside and outside. If we're to look at a muscle, what we're doing is that spontaneous release of the phosphate is coupled to a non-spontaneous contraction of that muscle fiber. And so again, it's not like we're using electricity, it's not like we're using light, we're storing energy in molecules and then we're simply coupling that to exergonic reactions. So did you learn to explain how external energy and energy coupling can be used to drive endergonic reactions?
Okay. Sorry, this face. So this one is showing how, you have a non-thermodynamically favored reaction, you have a thermodynamically favored reaction, or spontaneous and non-spontaneous. When you couple them together, so it's like a domino effect, and when it happens, it puts off enough energy to give that second one enough ump to get started through the required activation energy. So explain how external energy or reaction coupling, either, those are two different methods to force a secondary non-thermodynamically reaction to occur. Thumbs up? Good, good. It's just a lot of words, a lot of explanations. You will be asked to explain, let's see, there's 6 FRQs on your test tomorrow. The last one asks you to explain stuff with this information. Okay, so it should be kind of fresh, and if you want to watch the video, it's all you. Alright, so let's check our multiple choice. Can we do that? I use a colorful pen so you can go back and study. Study smart. Study the things that you've missed. If you got it right the first time and you were confident in that, then hopefully, you still know it. So, studying smarter and harder, sometimes they mesh, sometimes they don't. So I'm just going to roll through these. If you need a colorful device, Alright, and there's a couple on here where I think I gave 2 answers that I was okay with. There's only a couple. Alright, so 1A, 2E, 3D. Are we okay? I'm sorry. 1A, 2E, 3D. Because B doesn't include the B concentration. I wrote that down for myself. Okay. 4A, 5B, 6C, 7A, 8C, 9E, 10D. How are we doing so far? 11C, 12D, 13B, 14B, 15, I'm sorry, did I just say 15? Yeah. 15B, 16E, 17A, 18B, 19D, 20A, 21E, 22A, 23E, 24E, 25C, 26E, 27B, 28B, 29B, 30D, 31A. Alright, look at the one, oh yeah, 27 is B boy. Oh, yeah. Look at any other ones. You can answer by yourself first, and I'll do this one boy. I'm gonna do 27, I think. See what you got out of 31. Mark your score at the top so I can see how well you did. This is a personal reflective time right now. Personal reflection time. Grace. 27?
Yeah, I put E because I thought it would be sometimes D. That's not what it's choice.
Yeah. No, you're look at your slow reaction.
Well, because I mean you have 2 figures.
I remember what I did. We had different answers. I'm like, oh yeah, what you did great.
Yeah, I do that all the time. I like to write.
But what it would still be 2 in there too. I mean, that's just to figure out the overall reaction.
So,
How do you know you can't
so I
spell
had,
it?
I
Okay, so you still. Okay, gotcha.
So just a
I can keep going over questions you guys can ask each other. I don't care.
what it is. Come out and apologize. Just
Because, yeah. Did she just answer that? Thank you. Yeah.
So the ratio of, oh my gosh, the ratio of.
I don't know why I'm free.
Reactions from because all the reaction is independent of the concentration of hydroxide. Because the rate of reaction is the rate law, right? So if the slow start is step 1, the rate law is concentration. So it is independent of hydroxide. The rate, the amount of hydroxide that goes into step 2 doesn't affect how fast it goes. It is still required for the reaction to occur, but it's not. The rate of the reaction is not dependent at all on the hydroxide. Can you explain
if step 1 is found to be slow.
3? I'm going over number 3 if you want to listen. If you need it, the rate law that represents a reaction where doubling the concentration of A and doubling the concentration of B lead to a fourfold increase. What did you say?
I said B, but I think I understand.
Okay, because
Yeah, I understand.
Because even if you do double B,
Well, I mean, that is really good.
yeah, you have to get information. But it would have to say
The same
C is. I originally had B and I thought B was a better answer. Actually, I had B and B on that because they don't give you enough information. When it says in green, all of the variables constant, it should fit like or different concentration, this constant. So I would give you side effects for that.
No, I put C. Why wouldn't you use number 3? Because I put C as number 3.
So what's the rate of it? And then, yeah, just the so if you increase the is the second, and half that. Like put a double, like put the double D in. Would it be double D and half D would be? No, because one is.
So you just have to keep in mind
So it's just
equilibrium.
That's not always true.
It's not, okay.
So it's just for fast equilibrium, that would not be.
I
had to write it out. Really? I don't know if it's so funny.
If you guys are waiting on me, we're going to start the quiz in about 5 minutes, but if you want to work on your unit review or your graphing worksheet, if you've got all the multiple choice right, start out for a minute while I still answer questions.
So, did you get 17? Oh,
Okay.
Because what is that? So basically what happens?
your overall slow stat because your rate Oh no, it was my and then the first one like matches the equilibrium, but it was just like the first one goes
So you see that the production of and then it's always positive.
Alright, guys, if you need it, if you need a phone of some sort,
Okay, I have a question about, how do you know
know, like those experts and stuff have like the fold increase. I know it's like.
So what's the other point?
Yeah, like so like I did the A and B, but I didn't but I get to come back with Oh my god, I got that wrong because I was looking. I thought we were doing a problem like coefficients and that was the response. Okay, we're just gonna come to the
Yeah. So it's mostly in the notes. So if you can put something that I made up in the notes,
No.
or in like the last note, but I'll show you how I did it. So like, what do you have to say? I just have to okay. So first we find. Alright, so most of the polarities you got in your graph, so like,
so then I guess I messed up.
that's like one is like point over and then for this one you got to say like ours was 20, so it's 10. So it's 0.8 for all of them except for two. I got the two and one double. I want to say
I don't get the whole perspective.
What question are you looking at?
Well, I did first and
Because you're saying.
26.
Oh.
It's like a whole.
Wait, let me
double.
I told you I got.
And I went to max, like with perspective too.
Oh my god.
Why is it just
When it's so high,
yeah, so like for these ones it's 0.2.
my mom was
Yeah. 0.001 more.
24 the rate on two equation, the coefficients would correspond to.
And the rate and so for the rate you do changing concentration over rate time.
So that you can only have the flow stuff for in a mechanism. Okay. Yeah, I missed you.
If you have another question, raise your hand. I'll come to you.
0 minus
Why?
and then you don't put negatives.
Huh? I'm sorry, what?
Do you put negatives in the rate? You don't do that.
Oh.
Wait.
You're like
Computers. This is counting as your quiz.
Oh, JK. Oh, so this is
It's no. It can be a loud quiz, but no. You're still doing it individually. Can I answer? Can you rephrase your question?
did you say that you make rates negative?
Right. You never write a negative in front of the rate because you would say it is consumed or the rate of consumption of something is this because the rates themselves are not negative.
Okay.
All right, so guys, if you don't know how to use Kahoot, I'll explain it now, but this is counting as your quiz grade, and I just thought it would be a more fun way to do it. It is individual, but you can still be like competitive and, throw chairs and stuff if that's what you got to do. Speed helps you get more points, and I usually will give extra credit or more money for the top dogs in the Kahoot system here. But if I'm going to look at the grade itself, like to see what percentage you had correct. Okay? And I'll read it out loud for you, okay? So if those of you in the back can't see something, I'll read it out loud. Okay, so what you need to do is go to kahoot.it, and it's going to say that right now. So here we go. I'm going to tell you, it's going to pop up. I have no idea what the game pin is right now. I'll have to launch it first. Gosh. Real loud. All right. Here we go. When you go to, it's good. I won't start it until you're ready. Promise. When you get on there and you go to kahoot.it, Type in the game pin 1755.
Do you mind if I put Beyonce?
I don't know who it is. It's okay. Now, one of you guys would No, that's usually my name.
Oh, he put
Wait,
what?
I just don't know that you want
Okay, I'm gonna do auxiliary. I'll do the same.
Am I the Grace? Am I the first year or the second?
I'm the second.
I'm
Dag. She's the G of Dag.
And you know,
Game pin 17.
I'll do my shirt.
585.
let's do Chris.
I sure hope I know who this is.
No.
I'm playing too. It's interesting. I'm gonna go really slow though, okay? I'm not one of you guys.
That's great.
Oh,
I bet you.
It's checking your
Grace, you're
name.
so funny.
Is it illegal or something?
I don't know.
I sure hope I knew who these people are by the time I start grading it. Pen so low.
That's you, Mom.
Hansel, are you Beyonce?
No.
Is it up there?
Oh my god.
Oh, there's two good guys again.
Yeah. She did it last time.
Is everybody up here? Let's roll. 21 questions. Are you ready?
No.
Collisions between particles can produce a reaction if there is the correct.
It's all.
You can't see. I might have to I might put you guys apart. Let's go for the first one.
Oh my god.
I'm going to speed this thing up. Jeez, there's 17.
I knew it.
I'm going to do my people a favor. You guys can't see in the back. Okay, we'll try one more like that. And now I'm
I'm fine with
Let's do this.
Daniel.
Are you back? You have fight. You
I don't want to know who that one person is.
That was me. I'm prepared.
Awesome.
I promise you.
For the reaction below, the rate law is equal to K times x times y. Which step is the slowest? The rate law is x times y. Okay, so if the rate law is rate is equal to k times x times y to the first and to the first, then these stoichiometric numbers go up to, stoichiometric numbers go up to exponents. So how did we step one? Because they were the only ones with x and y as reactants. Rate law is the rate determining step. Dun, dun, dun.
Can I test you like this?
No. The rate law for a reaction is determined to be rate is equal to Ka squared B squared. What are the units of K?
Yeah, I think I'm right this time. Oh, I should have not.
Oh, man, no!
Okay.
No! It's real negatives.
Wait.
Alright, two more people.
I'm thinking.
Oh,
I can't remember.
here we go. 5, 4, 3, 6. Okay, so basically, if you have your reactants to the overall fourth order, one of those polarities have to drop down, so it's not the fourth, it should be the third, but then you have to go to the denominator to cancel them, so that's be into the negative third. And then seconds, of course. For a solid to react most quickly, it should be added to the reaction in the form of. I'm gonna wait. Okay, we got like 20 seconds. Oh, after it's And 5, 4, 3, 2, 1, go. 5, 4, 3, 2, 1. I'm gonna have to test you. Yes, good job, Hansel. Good job.
No, great.
Ready, set, go. Catalyst lower activation energy of a reaction by.
Oh, I want to see it.
You have 10 seconds. You're not getting a full minute. That's ridiculous.
I need to button this. Are you sure?
Okay. Yes, providing an alternate pathway. I don't know who you are. Okay. I will know later. For a reaction between X and Y, data below was obtained. What is the rate law for this reaction? What? Oh, it's in your head. Let's see. Hey, that's pretty good ratio right there. You can do that in your head, right?
Yeah.
Okay. So no calculator on that multiple choice. You'd be all right. You saw like one of them doubled and then caused the rate to quadruple, so it had to be in second order, and then one of them doubled and caused the rate to also double, so it had to be in first order. That. Okay.
Miss Emma, you can't be up there on the top.
Was that up there?
Yes.
I'm so sorry. I was trying to slip.
I'm so horribly bad at these.
Increasing the temperature at which the reaction occurs speeds up the reaction by.
Oh my gosh. What is these?
That means two of them are right. It just says that two of these are correct. That's what it says. Okay. You have 10, 9, 8, make choice. Jaws is coming. Oh, is it? Okay. Two of these, yes.
Yes, I moved up.
Remember that, what's it called? Temperature affects two factors. Okay, cool. I just turned it down so it was loud. The reaction A yields B plus C is second order. A linear plot will result when time is plotted against. Yes, when you 12 people rock, 4 people drool. A possible mechanism for any given chemical reaction.
Possible mechanism. Possible mechanism. It's always took at least 4 steps.
Give like 5 more seconds. I don't know. 5 more seconds. This is a random fact. Random fact. Random rate laws or rate mechanisms can only be determined experimentally. That's why we have to do some experiments, and that's why you're always given data. Okay? Because you're not going to get up in the middle of the test and go do that experiment. For the reaction below, which species is an intermediate?
Oh, I'm good. I was like, Z.
Yes, we all should have that for show.
Yes, now in 14th place.
Which is true for the catalyzed and uncatalyzed versions of the same reaction?
I can't project.
Yes. Okay, what did you guys, so we had a lot of people choose 5. Just note it says the E of the reactants is higher for the uncatalyzed reaction. So it would have to say something like the activation energy, so it doesn't have to specify reactant, but it should have said EA there. I could have said 2 answers on that for you. Okay, in a reaction that is first order with respect to X and first order with respect to Y, which of the following changes will have no effect on the overall rate? Right, you have like 3 seconds. Really slow. They negate each other. That was quadruple the rate. That was quadruple the rate. I'm not going to answer anymore. In general, rates of reactions that are slow are generally related with which of the following? I'm not going to answer until everybody else is
No.
Yeah, I will take you. I will pressure you and
After the quiz, goes Miss Walker.
What?
After the quiz, goes Miss Walker, not you, Zoe. Okay, so this one makes sense because low concentrations, low number of collisions, number of collisions, lower rate of reaction. All these other ones would yield a higher rate of reaction. Yes? Okay. Allison, what would cause a change in the kinetic energy diagrams as shown? Notice the difference in the line there. I don't know, you should do that.
Allison, you can still go. Come on.
Okay, so that line, I don't have the image back, but you saw on the lower axis of that was labeled kinetic energy, but the line moved back. So the activation energy, which is what that line represents, was lowered. So more of the collisions were able to meet activation energy, due to an alternate pathway, which would allow for the reaction rate to increase. If it had said increased temperature, you could have chosen that as well. In the pic below, what distance corresponds to the activation energy for the reaction of X2Y? Activation energy. Shh, I can't think. Alright, good.
I'm significantly.
Yeah, no comment. I'm not sure who did this, but you've got to look at the energy of the reactants up to the transition state, and that's your activation energy. Man, I'm waiting till the last minute. I think a bunch of you guys do this wrong. What is the rate constant for a first order reaction for which the half-life is 85 seconds? Graph doesn't matter. If you have a calculator out, I'm cool with that. It's just a half-life. Yes.
I'm off by so much.
Oh, yeah.
How many questions are those?
It's long, but it's not like an influence to that. Or you know,
Alright, you have 5 seconds, last person, 5 seconds. Yes, okay. Oh! Let me tell you how let me tell you can do it mentally. So what was the formula used? What is number 2 equal?
0.693.
Okay, so 0.693 over 85. When you rearranged your formula, so 0.693 over K is equal to 85, which is your half-life time. 0.693 over 85 is equal to K when you rearrange, yes?
Yeah.
All right, so 85 is about 100. I'm just rounding, okay? So 0.693 divided by 100 would be, to move the decimal back, how many spaces? 2. So it'd be 00693, right? So 0.00 anything was only this answer here. So that's how I did it. No, you can do it mentally if you can estimate something divided by 100, which we all should be able to. What point in the potential energy diagram given below does the transition state occur?
Whoa.
One more person?
That's me. I can even read the question.
Oh my gosh. You see his face? Transition state. The amount of energy needed to start the reaction and make products is called.
Wow, this is a hard one. I think I got it wrong.
Cool. Activation energy. Good. Thank you. Thank you. As the number of effective collisions between particles increase, the rate of reaction. Yay! Okay, that's easy. We got this. Yay! Which energy diagram below represents an exothermic reaction that has a small activation energy? It's cool. I'm waiting.
I know the rest is not the
that does help. Yes. I think that's right.
That was me.
I disappeared.
No!
Yeah, I like logged out. Whoopsies.
Is this it? Is this the end?
This is not okay.
I'm not okay with this.
Oh, we're okay.
It
Which graph
locked me
corresponds?
out.
Get back on. Which graph corresponds to the change in concentration of a reactant that is first order?
I just think, oh, I might have. I don't know if I'm in a good place. I'm not forcing anything.
Okay, let me tell you why. So that graph, what were the axes?
Oh, I didn't.
Okay, concentration versus time. Listen, if it was concentration versus time and it was zero order, what would the graph look like? Straight and then a negative slope, right? A linear graph for zero order. If it's a first order graph, but it's still the same axes, it's not linear. But you know that the general slope of any reaction, because the reactants are being consumed, is going to be negative. But it's a different, it's not a straight line. It's a radioactive decay. Radioactive decay. That's what I was trying to get to. Okay, I think this is the last question. But let me see. Yeah. And okay, Zozo, and then let's see all of them.
There's gonna be another
I'm
person.
literally 13 behind him.
Final results.
13.
I can't see any more. Oh, Mr. Brown. I will download all these, but we'll look at these. Okay. So let's do independent time real fast. What was on my to-do list here?
I learned.
You guys work on the graphing worksheet and the unit review the multiple choice that correlates with chapter 13. So we've got about, actually pretty good, about 40 minutes left. Well, what things we get done?
I'm gonna check some
Okay, will you put my water bottle?
This is logged me out. I just like put my name on it. So the 17 right. But I answered it right. So
Yeah, so